Today we're going to finally solve an example after a long time, and this is going to be for a single phase circuit. In the last video we derived some equations for the inductance of a circuit with two conductors in the single phase circuit, conductors X and Y, composite conductors with current in one going in one direction and in the other coming back in the opposite direction. If you haven't seen those videos, I would really encourage you to please go ahead and see that. I'll do a quick recap here, but all of these formulas will talk to you a lot more once we solve the examples today. They'll give you a clearer picture of how to use them. So, a quick recap. Last time we saw that the inductance of one of the conductors X can be given as 2 into 10 to the power minus 7 ln GMD X of Y over GMR X. So GMD was the geometric mean distance between X and Y, and GMR was the geometric mean radius of conductor X. Similarly, L of Y was nothing but 2 into 10 to the power minus 7 ln of GMD Y of X over GMR of Y. And then L the total, and these Lx and Ly were the inductances of the per conductor, and L the total inductance of the circuit was given as Lx plus Ly. GMD was nothing, so GMD X of Y or GMD Y of X is the same thing. It's the distance of each of these of the strands in this composite conductor to the strands in the other conductor. So it was nothing but a product of all these distances. So GMD X of Y was, and we saw that pi is a function similar to sigma that defines product. So it's nothing but the product of all the distances from for the strands in conductor X to the strands in conductor Y. GMR, the self GMD or the geometric mean radius, was nothing but a product of all the distances between the strands in the same conductor. And GMR was raised to the power 1 by n square, or a root of 1 of n square, where n is the total number of strands, and GMRY was to the root of 1 by m, to the root of m square, or to the power of 1 by m square, where m is all the strands in conductor Y. GMD was obviously to the power 1 is to the power m by n. Again, as I mentioned, once we do the example, all of these terms, all of these values will become a lot clearer. So just have that patience. Let's go ahead and solve our first example. So let's take a composite conductor. Let conductor X have 3 strands. So you have strands 1, 2, and 3. Let the distance between strands 1 and 2 and 2 and 3 be 5 meters. Or let me actually first draw the conductor around them. Let me go ahead and draw the conductor around them just to make it clearer for you. And we'll try to keep it circular the best we can. So that's conductor X. And then we're going to have conductor Y. Let conductor Y only have 2 strands, and let me draw them a little bit bigger because I'll make the radius of these strands different from the radius of strands in conductor X. So that's your conductor Y. So this is conductor X, this is conductor Y. Let this distance between 1 and 2 and between 2 and 3 be 5 meters between conductors X and Y, or rather between these two strands. Let that distance be 10 meters. So here you have strands 1, 2, and 3. Here you would have strands 1 prime and 2 prime. You have these distances. Let the radius here, so radius of each of these strands be point, let's say 1 centimeter, and for each of these strands here, let that radius be, let's say, zero point 0.5 centimeters. So you have all this information. Now let us find Lx, Ly, and L. So the solution of this, now we start plugging in all these values, and you'll start seeing the results and how to use them. So Lx is nothing but 2 into 10 to the power minus 7 ln of GMD over GMR. So what we realize is we have to find GMD, so that's the distance, geometric mean distance between these two conductors, and we have to find GMR for each of the individual conductors. So let's begin by finding out what would be the GMD. This is y of x is the same thing. We know by this formula that that's the product of the distances from all these strands in conductor X to all these strands in conductor Y. So in essence, that is nothing but d of 1 to 1 prime multiplied by d of 1 to 2 prime, then d of 2 to 1 prime, and then d of 2 to 2 prime, then the distance from strand 3 to 1 prime, and then the distance from strand 3 to 2 prime. So that's all the distances from all these strands in conductor X to all these strands in conductor Y, a product of them raised to the power 1 by mn. So let's do that. M in this case is 2, n is 3. So let's say 3 times 2. Let me write that here too. So the number of strands here we know is 3, and we know the number of strands here is 2. So that's your m and n values. Now, coming back here, d 1 to 1 prime, this distance is the same as that for d2 to 2 prime. Remember, these are all in straight line. That's the way I've drawn them. So these distances are the same. So d of 1 to 1 prime is equal to d of 2 to 2 prime, which is equal to 10 meters. Then, so that's 1. The second one is d of 1 to 2 prime. 1 to 2 prime. This distance is going to be the same as d of 2 to 1 prime, as well as that's going to be the same distance as d of 3 to 2 prime. Do you see why that is? This is nothing but a right angle triangle, right? If you imagine this is nothing but a right angle triangle here. Maybe I should have chosen a different color, maybe yellow. So this is a right angle triangle here. And this side is going to be equal to this side, and the same thing happens here. So that distance is d1 to 2 prime. That distance is from 2 to 1 prime, and from 3 to 2 prime. So you're going to have the same distance for d2 to 1 prime is going to be the same distance as d3 to 2 prime. And that is going to be nothing but the Pythagoras. And you're going to get the value as 11.18 meters. I hope that's clear. That's just very simple geometry. And then you have the distance d3 to 1 prime. So that's that distance, and that's again by Pythagoras theorem. You will have here 10 meters, here 10 meters. So that'll be 10 square plus 10 square root of that, and that gives you 14.14 meters. Now, if we plug all these values in here, what you would get is your GMD. I'm just going to write GMD xy, yx is the same. So then that becomes 10 square times 11.18 cube times 14.14 just once. The reason this is square and this is cube is because there is two terms here, there are three terms here. When you multiply the same terms, you get the square and the cube. And this whole thing to the power 1 by 6. If you plug that into your calculators, you should get something like 11.20 meters. So that is your GMD. Let us calculate our GMR X next. So GMR X is nothing but a product of all the distances between all the strands in conductor X. So D1 to 2, D1 to 3, D2 to 1, D2 to 3, D3 to 1, and D3 to 2. Okay, so that's D1 to 2, D1 to 3 times D2 to 1, D2 to 3, D3 to 1, and D3 to 2 raised to the power 1 by n square. So n is 3, 3 square. Now here again we know D1 to 2 is equal to D2 to 3, which is equal to D2 to 1 and D3 to 2. So what do we know? We know that D1 to 2 is equal to D2 to 1, which is equal to D2 to 3, which is equal to D3 to 2, which is all equal to 5 meters. Agreed? This distance is the same as this distance, obviously. And this distance is also 5 meters. This distance is also 5 meters. So you have all of that. So we've covered for D1 to 2, 2 to 1, 2 to 3, and 3 to 2. And D1 to 3 is equal to D1 3 to 1. So 1 to 3 is equal to D3 to 1. And there is something I'm forgetting in here. And what is that? Okay, now the one thing you need to always remember is the number of products inside this bracket will always be equal to the product they're raised to. So this will all GMD will always have m times n products, and I mentioned that in one of the videos. So GMD will always have m times n n products or values, will always have m times n values, and the GMR will always have, in this case in X for example, would always have n square values, and GMRY will always have m square values. So here if you come down here, we only have 6 values, whereas n square, 3 square is 9. So what are we missing here? You also need to remember GMR also, there is this case, if you follow this formula, and that's why it's good to follow formulas. So if we had gone step by step and we had said, okay, dk1 n of 1. So what's d1 of 1? I'm missing all these self GMDs, right? So you're missing d11, you're missing d22, and you're missing d33. So this is actually d1 of 1, d1 of 2, d1 of 3, d22, d21, d23, d33, d31, d32s, where all of these, okay, let me change the color here, where d1 of 1 is nothing but r1 prime, which is 0.7788 times r1. We remember that? So that's what I missed. So let's account for that here as well. So let's cancel this out. So disregard this. So GMR is nothing but a product of all of these terms raised to the power 1 by 9, and now you have 9 terms in here. Okay, so coming back now, so you've accounted for d1 of 2, d2 of 1, d2 of 3, and d3 of 2. They're all 5 meters. We know d1 of 3 is going to be equal to d3 of 1. d1 of 3 is going to be equal to the distance from 3 to 1, which is 10 meters. So let's write that down here. So you've accounted for 6 of your 9 terms. The last term that remains is the d11, d22, and d33. Remember, they will also all be equal because the radius is the same for all of the 3 strands. So here we have d11 is equal to d22 is equal to d33 is equal to 0.7788. What did we say the radius was? We said 0.1. Remember, this is centimeters, so we'll convert that into meters. So you would have 0.1 into 10 to the power minus 2, and that should give you a value of, that's simple, that's 0.7788 times 10 to the power minus 3 there. So then this implies that our GMD is nothing but 0.7788 times 10 to the power minus 3 to the power 3. You have 5 to the power 4 with the 4 terms, 10 to the power 2, all of this raised to the power 1 by 9, and if you plug that into your calculators, you should get a value of 0.31 meters. So you have your GMR. Similarly, you can calculate your GMR Y, and you should get a value of 0.14 meters. GMR Y would be nothing but d of 1 prime 1 prime, d of 1 prime to 2 prime times d of 2 prime to 1 prime and d of 2 prime 2 prime raised to the power 1 by m square. M is nothing but 2, so 2 square 4, and you have 4 terms in here, so you're okay. So please remember, always check this, make sure you're not missing any values. GMD should have m times n terms, GMRX should have n squared terms, and GMRY should have m squared terms. So now we have our values of GMD and GMR. Now we can plug them into our formula, and let me just change colors here so you can get L of x is equal to 2 into 10 to the power minus 7 ln of GMD over GMRX, and L of y is equal to 2 into 10 to the power minus 7 ln of GMD over GMRY. So then that's going to be nothing but 2 into 10 to the power minus 7 ln of, what was our GMD value? 11.2. So you have 11.2 over 0.31, which comes from here, and that should give you an end result of 7.17 into 10 to the power minus 7 henries per meter. And similarly, your Ly is 2 into 10 to the power minus 7. Ln of GMD is the same, 11.2, and your GMR is 0.14, and that should give you a value of 8.76 into 10 to the power minus 7 Henry per meter. These are both obviously inductances per conductor. So then you get your inductance for the circuit as Lx plus Ly, and that is nothing but 15.93 into 10 to the power minus 7 Henry per meter. So that's the value you get. Double check this. I'd ask you to solve this example, see the values. This will give you a better understanding. I'm obviously going to leave you with a sample problem at the end, but before I do that, now here you saw that the distances that I gave were pretty unrealistic. There's not going to be 5 meters of a distance between strands in a conductor, and and then you have 5 meter distance between there and a 10 meter distance between the two conductors. That is not realistic scenario. What's more realistic is that you're going to have two conductors, let's say conductor X and conductor Y, and then the strands in here are going to be packed up. That's more of a realistic conductor, right? So the distances between these strands is not going to be very much in comparison to this distance here. This distance is going to be a lot larger. So in a realistic scenario, you will have GMD can almost be taken as just the distance between the two conductors, because that's going to be much larger than the individual distances between these strands. Okay, so GMR, and the GMR value is still prominent, and you can get that from a lot of the tables from a lot of the conductor manufacturers. So it's from there you can easily calculate what the inductance of the circuit is going to be. But it was important to kind of exaggerate the distances here, so you clearly understand where these values are coming from, and you don't kind of make the mistakes that I almost made down here, where you're missing this value D11. And that's why it's important to follow these formulas. If you follow the formula step by step, then you will not make that mistake, as well as if you remember this. This is key here. Okay, now before I leave you with a sample problem, I'm going to do one other quick example, and this is not really going to be so much numbers as much as what I'd promised when we started our discussion. So we started our discussion on single phase circuits with composite conductors, but I'd mentioned I'll use the same formulas to show you how we can solve for solid conductor. So imagine it's not a composite conductor, it's a solid conductor, similar to what we had been using in our discussions earlier on inductance. And the distance between these two is D. The radius here for this conductor is R of X, and the radius here is R of Y. This is conductor X, this is conductor Y. Again, still a single phase circuit. So this has current I going in, and this has current minus I coming out. What's going to be the L value here? Now in this case, what's your N? N is nothing but 1, M is nothing but 1. What's the GMD? The GMD is nothing but the distance between the two conductors. So we can say L of X is nothing but 2 into 10 to the power minus 7 ln of, your GMD can be replaced by this value D. And what's GMR? There are no strands in here, remember. So GMR is just the radius here. So then that becomes Rx prime. Not just the radius, but because to account for the internal flux, remember we did Rx prime. So N is 1. So as I mentioned here, in this case, it's just one strand. So the distance is just D11. And D11 we know is nothing but Rx prime. Similarly for L of Y, we have nothing but 2 into 10 to the power minus 7 ln of D over Ry prime. Now, if the radius of both these conductors is the same, if Rx is equal to Ry is equal to, let's say, radius R, Then we can write L as being equal to Lx plus Ly being equal to 4 into 10 to the power minus 7 ln of d, and then r prime, where r is the radius of both of these conductors. And that is how you can use the same formulas that we've derived for composite conductors and basically get a value for solid conductors in a single phase circuit. And that's all I wanted to mention to you before I leave you with a sample problem. So let's see. Solve this. I'd say solve the problem that I solved up here. Go through the steps again by yourself as well, but also solve the sample problem and let me know what answers you find. If you have problems, also let me know and I can try to help you out, but there shouldn't be any problems. It's simply plugging the values in. So let me, okay, for conductor X, let us have 3 strands, and for conductor Y, let us also have 3 strands. These are all in a straight line, okay? So that's our conductor X, and that's our conductor Y. Now let me give you the distances between here. So let this distance be a meter. It's the same distance here as well. So this is 1 meter. This distance, let that distance be 2 meters. Same as here. Let this distance be 2 meters. Let this distance between strands 1 and 1 prime, let that be 5 meters. Let the radius here of each of these strands be equal to 0.2 centimeters. And then the radius here in the strands here, let that be 0.4 centimeters. Let me just tag these strands. So you have 1, 2, and 3. And here you have strands 1 prime, 2 prime, and 3 prime. And I think that's all the information you really should be needing. So find out Lx, Lx, Ly, and L. Solve the sample problem. Let me know what the answers are that you find. If you have any problems understanding it, send me a quick email. No problem. And next video, we'll start talking about three-phase circuits now. So it'll get even more exciting. Hope everything was clear with single-phase circuits and the discussions before that. If not, feel free to leave your comments below. Send me an email, nimish@movingelectrons.com. Do subscribe to our channel and you'll keep up to date with all the latest videos I'm posting. All right, then, till next time, have fun, enjoy these problems, and I'll talk to you soon. Bye now.